Hi everyone, welcome to my presentation today. My name is Zheng. I'm a PhD student at Indiana University Bloomington, and this work is the collaboration with the Alibaba Group. Uh, the work is named as Detecting User Community in Sparse Domain while Cross-Graph Pairwise Learning. So based on the title, we can see there are several keywords. First of all, this work is for user community detection, and it is particularly on the sparse graphs. And to solve the sparse graph challenge, we use the cross-graph techniques and the pairwise learning techniques as well. And the detail of the information will be showed and explained in the later slides. So first of all, let's take a look at the outline of this presentation. In the beginning, I will introduce the intuition and the motivation of this work. Second, I will illustrate the detailed methods and show the experiment analysis. And in the end, I will point out some future work to do. Let's take a look at the intuition of this work. In real world, there are many applications around us. Some of them are very big, like Amazon. Everyone uses Amazon to log in and to purchase product. Some of them are very small, like a cosmetic application. They are new and lack of users. For a user, if they want to log in to a cosmetic application to purchase products, and they can either use to register a new account. In this way, the cosmetic application will have no user profiles, and it will be hard for it to identify user groups. Another way is that they can log in use Amazon account. In this way, they can also get access to user Amazon profiles, and which the information can be used to generate the user communities, which can help the application better identify user groups. However, in real world, the user activities in Amazon are very messy and even noisy. So it is also necessary to generate some filtering techniques to only use the appropriate information from Amazon to support the user community detection in cosmetic applications. And here, that's the reason why the cross-graph community detection is important. And the challenge of this work is from three parts. So first of all, we want to do the sparse graph community detection. And the graph actually is a user product bipartite graph. It's not a homogeneous graph. And second, and last, we need to run a cross-graph propagation approaches to identify user communities. And to solve these challenges, we come up with some solutions. So first of all, we involve external information with designed filtering mechanism. And second one, we only focus on user node community detection and leave out the product community node community detection. And instead of generating user communities in the whole graph, we leverage user pairwise relationships to focus more on the local structure. And in the end, to learn the node community distribution, we design our own community recurrent unit, which is a very novel module in our framework. In the end, the goal of this paper is described as given a user I and its associated triplet user ijk, we aim to predict their pairwise community relationship, such as compared with user k, user j should have a closer, similar, or farther community closeness to user I. And here we introduce the detailed method of our model. So it includes the following sections. So first, I will introduce the overview task and to explain what the input and output of our model. And the following four sections will be the details of our model. And in the end, we also have some particular training strategies to make our model performs better. So in the task overview, first of all, the involved tasks involved graphs are two graphs. So the first one is the target graph, is a sparse graph S, and main graph M, which is the dense graph, which offer auxiliary information. In our previous case, the target graph will be the cosmetic graph, and the main graph will be the evident graph. The model input is a user triplet, user IJK, and the model output will be a pairwise community closeness label. The label in sparse graph S, the label, there are 3 types of the label, which is a similar, closer, or farther. And to define the labels, we have the following definitions. The similar relationship means that the user J and K are either in the same community or different communities with user I. The closer relationship means that the user J and user I are in the same community, where user K and user I are in different communities. The farther relationship means that the user J and user I are in different communities, while user K and I are in the same community. Meanwhile, we need to point out that our model is trained on mutual user triplets, meaning that all the involved users are appeared in both graphs. The model architecture contains 3 modules, including the user propagative representation, community recurrent unit, and pairwise community detection. So in the first module, we learn the users' representations through 2-level filtering and some extra information. And after we get the user representation, we pass to a community recurrent unit to learn the user community distribution. And in the end, the user's community distribution will, in both graphs, will be combined together for the final pairwise label prediction. And the details of the models will be introduced in the following slides. So first of all, the raw community detection is a pre-processing step. It uses InforMap, which is an existing community detection method, to generate raw communities in main graph M. The reason why we do that is that main graph contains very dense connections, and we want to make full use of such information. And this step offers a community level information for graph M, and also offers a community level filter for propagated information from graph M, which are circled in the red box in the below. And we will further explain how this module information worked to benefit the whole model. The first module is called user propagative representation. It contains 2 filters. The community level filter is only worked on the main graph, and the node level filter works on the both graphs. And the input of this, our model is a multi-hot embedding of the product. For example, the figure shown below means that the input is 1001, meaning that the current user is connected with product 1 and product 4 in the graph, and each product will have embedding associated with it, and the user embedding is calculated as the weighted sum of its related product embeddings, and the weight is calculated from the 2 filters. So for the community level filter, each product in the main graph also has a community label, and each community will be associated with a weight. In this way, the weight will be originally regarded as a community level filter weight, and the node level filter is based on a attention mechanism. We initiate and optimize a context vector and use the context vector to define the weight of each product embedding. And in the end, the node level filter weight and the community level filter weight will be multiplied together and normalized to identify the final weight of each product, and the sum of their weighted embeddings will be regarded as the final user propagative representation. And In the end, the output of the first module will be the concatenation of three parts of the information. First, is the user representative, user propagation representation. The second part is the original multi-hot product embedding, and the third part is the raw community embedding. And this third part will be concatenated together to generate the final user representation. And after we get this representation, it will pass to a community recurrent unit circled in the red box to generate the user community distribution. And the CRU contains two gates. One is the community affiliation gate. It helps to learn the user community detection. And another gate is a community update gate. It optimizes a community embedding given with the help of the user input. So each community, here we have a memory to store all their communities, all their embeddings. And given a user, based on the user embedding and the current community embedding, we learn the user similarity or affiliation score to the current community. And then for all the communities will be naturally form a vector as a community distribution. And each dimension in the community distribution is from 0 to 1. And for the community update gate, so each community embedding will involve partial of the user embeddings to update its embedding through a set of the functions. And to make all the communities are independent with each other, we add a community constraint as well. So in the end, the output of the second module will be the user's community distribution, and the pairwise user community and distributions in both graphs will be combined together to predict the final community closeness label in the pairwise community detection module. For pairwise community detection, we define the ground truth label y ijk equals 1 divided by 2 times 1 plus sjk. In terms of the community closeness for user I, if user j is closer than user k, sjk equals 1. If user j is farther than user k, sjk equals to -1. If they are similar, sjk equals to 0. In this way, one convert the pairwise ranking task to a regression task. And the user pairwise representation is calculated separately in each graph, either in S or M, which are concatenated later on for final label prediction, as we introduced before. The final loss is the weighted sum of the cross entropy loss and the community constraint. We have 3 training strategies. First one, the shared weights for users. We have shared weights for all users in separated graph. Second, the community memory is updated by taking the average of the 3 updated community representation in each user triplet. Remember, the model input is 3 users, so the community memory is updated once using the 3 users information. And in the last, we have a masked training strategy to randomly remove a small ratio of connected products from users in the main graph during each training batch. In this way, we can make our model more robust to the main graph app. And the next section, we will introduce our experiment analysis. It will include the following 6 components. The first one, we will introduce what is our dataset. And second, we will run the model comparison and do an ablation study to evaluate the effectiveness of all our model components. And we also run the analysis on different user types and explore the graph sparsity influence and do a case study in the end. Let's take a look at the dataset used in this paper. We collect 1 week's behavior data from from Alibaba user logs. The ground truth label is calculated from the whole data set, and the training data is the first 4-day behavior data. The pseudo community label for training is generated from agreed community structure from all baseline models on the first 4-day behavior data. And in the end, we construct 2 cross-graph dataset. One is a shopping graph as a main graph, and the news graph as a sparse graph. And another dataset is using shopping graph as the main graph and the cooking graph as a sparse graph. In the end, we have over 2 million user triplet in the first dataset and 200,000 triplet in the second dataset. And the details of the dataset is shown in the table below. And we also compare our model with 7 baselines. They are all community detection models from all perspectives, and the seven baseline models run on either main graph or sparse graph, or on the combined main and sparse graph. And compare with all the baseline results, we can see our model still performs the best among all the possible outcomes in the 6 reported metrics. We also run ablation study to see whether each of our model components are useful or not. The performance differences on all evaluation metrics between each ablated model and the original model is shown in the table in the red part of the slides. And there were 6 components in total. From the results, we can see that removing the node level filter results the largest decrease in the model performance, and the directed transformation representation has the least influence on the model performance. We also run a user type analysis because in the 2 graphs, there exist 3 types of the users. The first type is mutual graph users, where users appeared in both graphs. The second type of user is the users only appeared in the main graph, and the last type of users is the users only appeared in the sparse graph. From the 2 data sets, we can see the reported results in the 3 types of the users shown as below, and the mutual users has the best performance result because it has more user connections to the products, meaning that they have more information in the 2 graphs. That's the reason why it is works the best. And from graph sparsity influence, we can see that we intentionally keep partial connections in sparse graphs to see how well our model can handle cold start problem. From the reported 6 metrics, we can see that denser connections can lead to better evaluation results. We also do a case study on 3 sample users, where from the behavior keywords, user 1 and 2 are more similar than user 3. From the generated community distribution, user 1 and 2 are also more similar than user 3, meaning that our designed community recurrent unit works well. In the end, we point out some future works to do. For example, we omit the pseudo community label generation or merge it into a whole pipeline. We also need to involve more information into current model, such as user textual profile or session-based behavior history. Besides user nodes, we can also enable product nodes community detection in the future and run models in multi-graphs instead of 2 graphs in current scenarios. And that's all for my presentation. Thanks for watching.